In this lecture, we explore how modern physics understands time. In classical physics, Newtonian mechanics, time was absolute and the same for everyone. But Einstein's theory of relativity showed that moving clocks run slow and time itself can stretch. We will see that the key to understanding time lies in both relativity, time dilation, and twin paradox, and thermodynamics, entropy, and the arrow of time. Under Newtonian mechanics, time is universal. All observers share one global clock. An event's time is independent of motion or location. This concept works well at everyday speeds, but fails at high velocities or in strong gravity. Einstein's relativity will replace this notion with a more subtle one. Einstein's 1905 theory of special relativity postulates that the laws of physics and the speed of light are the same in every inertial frame. A counterintuitive consequence is that measurements of time and space depend on motion. In particular, moving clocks tick slower to a stationary observer, a phenomenon called time dilation. We will derive the formula next. Einstein also showed that simultaneity is relative. Two events that are simultaneous in one frame may not be simultaneous in a moving frame. This underlies time dilation. If clocks tick differently in different frames, simultaneity must change. Thus, time is intertwined with space in space-time. Consider a light clock, a beam bouncing between mirrors. If the clock moves horizontally, the light's path is longer, a zigzag, but light speed is constant. Hence, it takes longer for one tick to occur, as seen by an outside observer. The moving clock ticks slower. This simple picture leads to the time dilation formula. Using the light clock geometry, Pythagoras, one finds c delta t squared minus v delta t squared equals c delta tau squared. Solving gives delta t equals delta tau over the square root of 1 minus v squared over c squared, equals gamma times delta tau, where delta tau is the proper time between ticks, time measured in the clock's rest frame, and delta t is the dilated time seen by the stationary observer. Thus, moving clocks run slow by factor gamma, the Lorentz factor. Relativistic time dilation is confirmed by cosmic ray muons. Muons have a short rest half-life, 1.52 microseconds, so classically, few would survive to Earth's surface. However, fast-moving muons are observed in large numbers because their decay clocks run slower by gamma. Earth observers see their lifetime extended exactly as predicted by delta t equals gamma delta tau, verifying time dilation. Atomic clock experiments also demonstrate time dilation. In 1971, Haffel and Keating flew precise clocks on jets around Earth. After the trip, comparison showed that moving clocks lagged behind Earth clocks by the amount predicted by relativity. Gravitational effects also contributed, but even SR's effect was clearly measured. This real-world test confirms moving clocks run slow, not due to instrument error, but due to time itself changing. A famous thought experiment is the twin paradox. Twin A stays on Earth, twin B travels at relativistic speed to a star and back. According to Earth, the moving twin's clock ticks slower, so twin B ages less. For example, if gamma equals 30, A 2-year round trip for the astronaut means 60 years pass on Earth. On return, the space twin is near 42, while Earth twin is near 100. This seems paradoxical because each twin sees the other moving. Where is the asymmetry? The traveling twin changed direction, accelerated, to return, switching inertial frames. The Earth twin remained in one frame. Thus, the two experiences are not symmetric. Special relativity explains the result. The space twin's frame is not inertial throughout, so she ends up younger. There is no real contradiction once we account for the acceleration and relativity of simultaneity. In detail, the traveling twin's clock follows a different space-time path with a turnaround. Mathematically, her proper time between departure and return is shorter than Earth twin's coordinate time. In short, the twin who accelerates and changes frames ages less. Both special and general relativity give the same conclusion. Einstein's general relativity adds that gravity also affects time. Clocks deeper in a gravity well tick slower. For example, a clock at Earth's surface runs slightly slower than one on a high mountain or satellite. This gravitational time dilation was measured. For example, GPS satellites correct for it. Thus, both relative velocity and gravity influence how time flows. Practical systems must account for relativistic time effects. GPS satellites orbit Earth at high speed and altitude. Special relativity makes their clocks run slow, relative to Earth, but weaker gravity at altitude makes them run fast. The net effect is that satellite clocks tick faster by about 38 microseconds per day. Engineers must correct this, or GPS would be useless. This is a direct application of time dilation in technology. Switching gears, in thermodynamics, entropy measures disorder, or the number of microscopic states, omega, consistent with a macroscopic state. Boltzmann's famous formula, S equals K log omega, relates entropy to probability. High entropy means many possible arrangements, disorder. Low entropy means few, order. The second law of thermodynamics states that the entropy of an isolated system never decreases. Equivalently, it always increases or stays constant. This gives a thermodynamic arrow of time. Processes naturally go from low entropy, order, to high entropy, disorder. For example, heat flows from hot to cold, gas diffuses, and broken eggs don't unbreak. This distinguishes past from future physically. Consider simple processes, an ice cube melting, or ink diffusing in water. In each case, initial state, ice plus cold glass, concentrated ink, is low entropy, and final state, water plus warm glass, ink spread out, is higher entropy. We never see the reverse spontaneously. Our intuition and video examples show that only the forward direction increases entropy. This is why we can distinguish past from future by entropy change. At the microscopic level, fundamental laws, such as Newton's laws and quantum mechanics, are time reversible. A billiard ball collision or particle motion makes no preferred direction of time. Yet macroscopic phenomena show an arrow. The key is probability. Overwhelmingly, there are more high-entropy, disordered states than low-entropy ones. Thus, even though each microstep is reversible, the statistical trend is toward increasing entropy. Cosmology also reflects entropy's role. The early universe was in an extremely low-entropy state, nearly uniform hot gas. Since then, entropy has increased, structures, stars, and heat radiation. The second law suggests the universe will evolve toward equilibrium, maximum entropy, heat death. Our cosmological arrow of time is linked to this entropy increase from the Big Bang onward. The second law is statistical. There's an overwhelmingly higher chance to move from order to disorder. Occasionally, tiny systems can fluctuate to lower entropy, but for macroscopic systems, these fluctuations are negligible. Entropy and the arrow of time are emergent from probabilities of microstates, not absolute forbiddance. In practice, entropy only goes up in noticeable systems. Our psychological sense of time's flow matches the thermodynamic arrow. We remember the past, low entropy state, and predict the future, higher entropy. In example videos of a candle burning or a pot of water, only the forward direction looks natural, entropy increasing. This is why we never observe effects preceding causes on a macroscopic level. In summary, two main frameworks describe time in physics. Relativity shows time is malleable. Moving clocks slow down. Delta t equals gamma delta tau, and simultaneity is frame-dependent. Thermodynamics adds a direction. Entropy must increase, delta S greater than 0, giving time an arrow. Both are crucial. No clock ticks in every frame, and no macroscopic process spontaneously reverses. Physics combines these to explain how time really works. Let's highlight the important formulas. Time dilation, delta t equals gamma delta tau, shows moving clocks run slow. Boltzmann's S equals k natural log of omega connects entropy and microstates. And the second law, delta S greater than or equal to 0, defines the arrow of time. Memorizing these helps solve concrete problems and understand concepts. Some misconceptions. The twin paradox is not a paradox once analyzed properly. Time dilation is not an illusion or clock error, it's intrinsic to space-time. And entropy usually increases only in closed systems. Local decreases with greater surroundings increase are allowed. Clarifying these points keeps our understanding consistent with experiments and theory. Some theories, like the space-time block universe, suggest all times exist equally and the passage of time is an illusion. Others study quantum mechanics and gravity, asking if entropy increase ultimately ties to quantum measurement or gravity. While speculative, these ideas show physics is still probing the nature of time. For our class today, the key takeaways are: time depends on motion, relativity, and has a preferred direction, entropy. Understanding time has practical impacts. GPS navigation relies on relativity corrections. Particle accelerators must account for time dilation. Fast muons live longer to be studied. In thermodynamics, we design efficient engines by managing entropy. Even biology is affected. Our aging rates are minutely slower when flying fast or sitting in orbit. These applications underscore that time dilation and entropy are not just theory, but everyday realities. In conclusion, time in physics is not absolute. Relativity taught us moving clocks tick slower, time dilation, and acceleration breaks symmetry, resolving the twin paradox. Meanwhile, the second law of thermodynamics gives time an arrow via entropy increase. The combination means that while the fundamental laws are time reversible, the macroscopic flow of time we experience is determined by entropy. This deepens our understanding of time as not just a backdrop, but an active part of physical law. Thank you.